Hi, welcome to part 2 of my brief review of integration. What does it mean? What is it? How do I do it? So in this example, I'm gonna consider the following situation. I imagine I have a rod of a certain length, let's call it L, and a certain distance away from that rod, I consider a point here, and I imagine that this rod is charged up, so it carries a charge. Let's make it positive just to be concrete. There's a total charge Q that's equally spread out over the rod. So you can imagine maybe it's a rod of metal, a conductor, so the charge is going to spread out evenly across it. And I'm asking, what is the electric field due to this charged rod, and what's the electric field here at this point, a certain distance d from the end of the rod. So let's analyze this physically first. I assume you understand Coulombs Law. I assume you have a basic notion of what the electric field is. But let's see how integration then comes into this. So let's think about this. I have a positively charged rod here, and that's going to create an electric field over here. Right, there's a bunch of charges. Now, because it is positive, I'm fairly sure the electric field is going to point away from the rod. Right? So I can be fairly certain that the electric field over here going to point to the left. And just because every single part of the rod is going to create an electric field to the left. But how do I work out the strength of that electric field? Now, you might say, hey, let's apply Coulombs Law. Right? But the problem you run into is, while I have the total charge of the rod, I'm not really sure what distance should I put in, right? So let's write down Coulombs Law again. Right, Coulombs Law for electric field says the strength of the E field is K, the electric constant, times the charge Q, let me write it like this, divided by R squared, where R is the distance between the point where I'm thinking about the electric field and the point where the charge is located. Now this rod is not located at a point, right? It has an extension. Some of it is located here, some of it is located here, some of it is located here. So what should I put in? Maybe I should put in just the middle value, like L over 2, right? Halfway. But that's not gonna work, because this end of the rod, say, right, we probably all agree that this end of the rod has the strongest contribution to the electric field here because it's closest. This one has the weakest. But if you measure it from the middle, this one, the electric field due to this point, plus the electric field due to this point, doesn't average out to be essentially twice the electric field from the middle. That would only work if this were a linear function, if the electric field were a linear function in distance, which it is not. It's 1 over R squared. There's nothing linear about it. Right? So you can't just take the average. And, you can try that. I mean, try saying I'm going to have a little charge Q here. What's the electric field here? For a charge Q here. What's the electric field here? Is that equal to twice that charge, like, as if both charges were located in the center? The answer is going to be no, right? So you can't just take the center as the position of the rod. You have to consider each little bit of the rod separately and see how it contributes to the electric field over here. Let's write this down. Total E field, and I'm always going to mean at this point, right? Total E field It's all in the same direction, right? So at least I don't have to worry about components in this case, in this particular example. That is just the sum of the electric field due to each little piece of the rod. Oops, sum of, what am I doing? Sum of E fields, call them E field contributions, right? Each little chunk works together to make the whole. Sum of E field contributions due to individual chunks of the rod, right? Okay, so what do I mean by a chunk? Well, I can imagine I cut this rod up into tiny bits, right? And now I'm considering this little bit here, right? That is my chunk. And if I make this small enough, I can approximate this little chunk of the rod to be at a single point. So I'm going to split my rod up in 100 small pieces. Each one is small enough that I can reasonably say it's at a single point. It is definite position here, no real extension. I can work out the electric field due to it using Coulombs Law, and then I can add them up. And if I want to get a more accurate answer, right, it'll be a slight approximation. I might instead take 1,000 little chunks, make them smaller. And if it's still not good enough, I'm going to split up my rod into 1,000,000 tiny chunks. Work out the electric field due to each one, and then add them up. Probably not by hand, but I could have a computer do it for me. But, the computer would take a fraction of a second. So let's figure out then what is the E field contribution due to that individual chunk. So it clearly depends on which chunk I take, right? I take the chunk right at this end, the one here, one further along. So I guess we should be able to say where the chunk is. So let's put down a coordinate system. This is all along a line, so we only need one coordinate axis. So let's call this our x-axis. Let's say, this is my x-axis here, and let's just pick something. I'm going to say this point where the rod starts, that is the position x equals 0. That's an arbitrary choice, right? I made the choice. That's how I'm going to label positions in my setup. So let's figure out what's the electric field due to that tiny chunk. Right, so the electric field contribution, the E field contribution of the tiny chunk, well, let's apply Coulombs Law for electric fields. It's going to be K times the charge of the chunk divided by the distance of my point to the chunk, squared. I'm writing distance to chunk, I mean the distance from the point where I want to find the electric field to the chunk, squared. Now, because I have my coordinate system, I can easily write down what the denominator is here. It's just going to be d plus x, right? If this is at x equals 3 centimeters and d is 5, the distance would be 5 plus 3, 8. Right. So I can easily write this as x plus d. But what about the top part? What about the charge of the chunk? Well, the total charge is Q, 1 Coulomb, half a Coulomb, whatever it is, right? We just call it Q. But this little chunk is not the whole rod, so it doesn't have charge Q. Well, if it were half the rod, it would have half Q. If it were a tenth of the rod, it would have a tenth Q. If it's a millionth of the rod, it has a millionth Q. So I'm asking, right, what is the width delta x of my chunk? The fraction that is of the length, like 1/1,000,000th, well, that times Q gives me the charge of the chunk. So the charge of the chunk is going to be the width of the chunk, the delta x, divided by the length of the whole thing. So that is what fraction of the total rod is the chunk. Is it a millionth? Is it 1,000th? Is it a trillionth? Multiply that by the total charge. Okay, so let's write this equation again. What we just wrote down in words. Let's write it in symbolically. Because this E field contribution is just a tiny piece of a much larger E field, I'm going to write this as delta E, like little delta, meaning a small piece of the whole. It's going to be equal to K times delta X times Q, and then write as Q over L. I'm going to move the L from here over there. Divided by X plus D squared. This thing Q over L, that is sometimes called, well, not sometimes, it is called the linear charge density. It says how much charge do we have per length, right? This fraction charge per length, this is called the linear charge density, and it's sometimes written as lambda, like a lowercase Greek lambda. It's saying how many coulombs per meter. If you have a long cable, we don't know how long it is, we can still maybe say how many coulombs it has per meter, or per centimeter, or per light year. So let's now evaluate this expression. When I say evaluate, I mean, of course, evaluate the total electric field. This expression here, well, that's just what I got. There's nothing more I can do about this, right? But now I can take this and plug it into here, right? I take the sum of all the little chunks. Maybe you've got a finite sum, meaning a sum of, 10 little pieces. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or 100, or 1,000. You could literally just plug in values where the position of each one is going to be, right at the beginning, 100th along, 200th along, 300th along, 400th along, and so on. That's something a computer would do. If you program a computer to work this sort of thing out for you. But in our case, we want to be exact. So we're going to make our chunks infinitesimally small. So our sum becomes an integral. Right? Integral, remember, is a sum of infinitely many bits, each of which is infinitesimally small. And the electric field contribution due to one tiny chunk is going to be infinitesimally small because that chunk itself is infinitesimally narrow, and so it's an infinitesimally small amount of charge. So let's sum up our electric field. So the total E field is, well, let's write it out. It's the sum of all little delta e's, which is an integral, right? Remember, this is really just a sum symbol, big S, of all the delta e's, but now because I'm making them infinitesimally small, I'm just going to write it like this. And what am I summing over? I'm summing over all parts of the rod. And that's the conceptual thing I'm doing. I'm taking a sum over all parts of the rod. For each one, I take the piece, the contribution to the electric field, delta E, or now I'm going to write it as dE, because that's what, I guess, what the convention is. That is, as you go to infinitesimally small chunks, you'll turn your deltas into d's. This thing I can't evaluate, right? I need to somehow, like, what do I do with this? Isn't it? It's a mathematical expression, but how do I, actually get a value out of that? Well, I've got an expression for this, right? I know that dE, worked out up here, is this. So I'm going to plug this in. I'm going to get k times, the delta becomes a d. Right now my width of my chunk is infinitesimally thin. Q over L divided by x plus d squared. Something I want to emphasize in integration is like what your integration variable is. The thing that is the dx or dt, right? It's not arbitrary. It's not something you sort of decide. It follows from our setup. Right? The reason each of those contributions is tiny is because I pick very, very narrow pieces of the rod. My chunks are tiny. Right? This is where the infinitesimal aspect comes in. What are the limits? Well, I want the whole rod. Let's look at the picture again. Right? The rod starts at x equals 0, it ends at x equals L. So those are going to be my limits. And now I can perform the integration. Notice what's important when you want to set up an integration is that the thing that you sort of increase stepwise. In this case, I'm hopping from one chunk to the next, and each chunk is a little dx further along than the previous one. To actually perform the integration, you have to be able to express the limits in terms of that same variable. So in this case, the limits, the rod starts at x equals 0, it ends at x equals L, and I'm going from here to here by adding a little dx each time. Or little delta x, if it's small, finite, and not yet infinitesimal. Otherwise, I can't perform the integration. Right? I have to be able to express the limits, the range of my integration. What am I summing over? How do I know when to end the sum? I have to be able to express that in terms of the variable that I'm slowly increasing. In this case, x. And that's the same variable x, the position here, that also introduces the infinitesimal nature of this expression. Right? Everything is finite. Even any given value of x is a specific number. But this tiny, tiny thing here, right, that is what makes this whole thing infinitesimally small. And therefore, when I take an infinite number of them, I might actually end up with something that's finite. Okay, but let's work this out. Well, this is not a hard integral to do. I can take a bunch of stuff out front. K, Q over L, right? Those are all constants. The integral is between 0 and L. Again, I'm going to write a sort of shortened version for the limits, where I know x is my integration variable. What's left in here is dx over x plus d squared. Now, maybe you can just see right away how to integrate this. If not, you could do a substitution where you say u equals x plus d, but you don't even have to do this. This is fairly straightforward. I'm going to go k q over l. So what function differentiates to become this? It's going to give you the answer x plus d, right? Not squared, because now if I take the derivative of this, it's x plus d to the minus 1. Taking the derivative makes it x plus d to the minus 2, but when it started minus 1, I get a minus sign, cancel this minus sign, okay, I get back to this. This makes sense, right? If you can't see that this is the integral of this, then you should go back to your calculus textbook and do some problems or look over some old notes. My limits, I need to add my limits here. So the limits are 0 and L. You plug those in. I'm going to get k q over L times. Now plugging L in gives me something, plugging 0 in gives me something. Neither of them makes this term go away, so I'm going to have both. But minus 1 over L plus d, plugging L into here, then minus, because it's the other limit, minus 1 over 0 plus d, which I can conveniently rewrite as kq over L times minus minus makes plus 1 over d, because this is a 0, minus 1 over L plus d. That is my final answer. A special case of this would be where the rod keeps going, right? It never ends. L is infinite. You might say, doesn't it create an infinitely strong electric field over here? Well, it doesn't, even if the linear charge density is constant, so there's 1 coulomb per meter. I've got an infinite number of coulombs total, if it's an infinitely long rod. Even then, if you plug in L equals infinity here, but this fraction here is lambda, right? This is a constant. Plug in infinity here, well, that just makes this thing go away. It's still a finite value. But for the finite rod, this is our final answer. So I hope going through this helped you understand a little bit more what integration is, how do I use it, how do I apply it, when do I need to apply it, right? The fundamental reason we had to use it was because each tiny part of the rod contributed differently to the electric field because it was a different distance from that point. And no averaging or estimating or anything like that would have given you the right answer. You have to go through the steps of splitting your rod up into tiny chunks, and for each one you work out what's the contribution to the electric field here. Like, what's the electric field here if it were just that tiny chunk? And then you add them all up. And the adding them up, that is where you actually perform the integration. So I hope that helped. I hope that'll help you tackle some of the homework questions as well. And hopefully it'll also help you consolidate those concepts that you've met in your math courses before, but maybe haven't really seen many direct applications of outside of those math courses.